A very good morning to all of you, ladies, gentlemen, and the scholars of SNBNCBS National Center. I'm indeed very privileged to welcome you to the Foundation Day celebration of the center, which is being held today. So, this is just a brief history of the institute, which would like to present. So, the journey of the center began on 13th of June, 1986. When the center was registered under the West Bengal Societies Registration Act, with an exclusively goal to emerge as a seat of research in basic sciences, networking in the frontier areas. The name Satyendranath Bose National Center for Basic Sciences was chosen by the Department of Science and Technology, Government of India, after the great physicist, Professor Satyendranath Bose, and this was a way to pay homage to the life and work of a colossal figure in theoretical physics. In the last 36 years, the center has emerged as a major institution of research and development in basic sciences, especially in the areas of physical sciences and related disciplines. The center has also made significant moves in application-driven basic research in areas of national need. The center has advanced research and experimental facilities and an advanced manpower training program in the form of PhD courses, postdoctoral programs, active visitors and linkage program, and various other outreach activities. I would now like to request Professor Tanushri Shahadashgupta, Director of the Institute, to say a few words and also read the message we have received from Professor B.N. Jagtap, IIT Mumbai, and currently the chairman of the governing body of the institute.
Thank you, Shrini. So, very warm welcome and congratulations to all of you for this Foundation Day. We never had actually a formal celebration of Foundation Day, but I thought it would be a very good idea. In addition to celebrating the birthday of Professor Satyendranath Bose, which we do on 1st January, also to celebrate our Foundation Day. As our register has just now said, on these days, the society was registered and it started in journey actually in cultivation of sciences. And in 1987, it moved its base to the rented house of DB17. Some of you have, those who are from the old time, they know that place, spend time there. And the land where we are now was given to us in 1990. And the first, I think, the structure and the building came up in 1985. So it's a very long journey, but of 36 years, not really very long compared to all other PhD institute in this city we have, but long in terms of our frame of reference. Very, very successful, and it's a journey towards excellence. I do believe that. I think during our alumni meet day, there were discussions with, we had about 10 PhD students. From there to today, we have 170 PhD students. We have state-of-art experimental labs, computation facility, vibrant in terms of the manpower training, as well as doing cutting-edge research. So we have come a long way, and I do hope this path of excellence will be able to continue in this path, and there will be newer heights that we will be able to attain in coming days. So with these few words, Professor Jagtap, who is traveling currently, he is in Orissa, so he has sent a message to be read out. So his message is the following. Professor Tanushri Shahadashgupta, Professor Umakant Rapal, faculty, staff, and students of SNBNCBS Center, distinguished invitees, ladies and gentlemen, at the outset, let me greet you on the occasion of 36th Foundation Day of this center. Foundation Day is a very special day when we fondly remember the vision of our founding fathers, the commitment of the faculty members for the academic excellence, the dedication of non-teaching staff, and the passion for learning of our students. Knowingly or unknowingly, this day also reminds us to rededicate ourselves so as to take the Institute to still bigger heights. I welcome and thank Professor Umakant Rahul for agreeing to deliver a talk on Bose-Einstein condensation on this occasion. Predicted in 1924 and experimentally observed in 1995, BEC is one of the fascinating areas of physics. It has been breaking newer grounds such as quantum information, dark energy, gravitational waves, space research, subsurface, mineral prospecting, so on and so forth. I sincerely hope that today's talk by Professor Rahul will infuse us to develop a vibrant program in many of these advanced areas associated with BC. This will be befitting to the name of SN Bose associated with the institute. Finally, I take this opportunity to compliment the director, faculty, staff, and students on their continued effort to make this center a place of advanced learning in the country. Wishing the Foundation Day function every success, wishing you all the very best in your future endeavors. Thank you, one and all. So thank you so much, and I now request our registrar to introduce this.
Thank you, ma'am. I would now like to extend a warm welcome to Professor Umakant Rahul, Indian Institute of Science, Education and Research. Professor Rahul is an experienced experimental physicist with a demonstrated history of working in pure and applied physics. Skilled in experimental quantum physics, spectroscopy, and nanotechnology. He has a strong educational professional degree as Doctor of Philosophy focused in atomic and molecular physics from IISc Bangalore. Currently, he is leading a group of young researchers in the area of atomic physics, quantum optics, and quantum effects NAP technologies. I would now request Professor Rahul to deliver his lecture.
Yeah, thank you very much for inviting me here for giving this talk. And I would like to thank specifically Professor Tanushri Saha Dasgupta and Professor B.N. Jagtap for inviting me on this occasion. And I'm very honored to give a talk at the Bose Institute. Unfortunately, I could not travel. I would have come here in person and given the talk, but there were too many things happening simultaneously. Anyway, thank you very much for the kind introduction and inviting me here. So let me start sharing my slides. I hope you can see my slides. Yeah?
Yes.
Okay, fine. So it's an honor, as I said, to be talking about this Bose-Einstein condensate phenomenon, Bose-Einstein condensation phenomenon at the institute, which is named after the stalwart of physics who laid the foundations of, some of them very basic aspects of quantum mechanics and how particles behave. So I'll be telling you about what this Bose-Einstein condensation is about and how these things are produced in the lab, and how some examples about how the existence of this condensate in nature. Okay, so there are broadly, as we all know, there are two types of particles, the bosons and fermions. Both of them behaving differently in terms of the way, the kind of statistics they follow. First, the Fermi-Dirac statistics and the Bose-Einstein statistics. These two particles follow two different types of statistics, as we all know. The fermions are these particles which have half-integer multiple of spins, whereas bosons are integral multiples. I mean, they possess integral multiples of spin, and some of the examples of bosons are photons and composite particles like atoms, where the total angular momentum is what decides the total spin of the atom, in spite of the constituents having, constituents being fermions. And we know that as a function of this energy of these particles, the ratio of the energy of the particles to the chemical potential at different temperatures, the distribution function for the fermions and for bosons have a different kind of distribution. As you can see, there is for fermions, there is exactly one particle that can occupy a particular energy state as we go to lower and lower temperature, whereas there is no limit to the occupation probability of the number of particles that can occupy a particular energy state in case of bosons. Now, we know that, just pictorially depicting how these particles, these fermions and bosons can occupy different possible energy levels. Now, here I have shown something like a harmonic confinement potential, where if you take an example of, say, electrons with up and down spins, then you cannot have you cannot have more than one type of particle sitting in a given energy level. So, for instance, in the ground state, for instance, you can have exactly two particles of opposite spin sitting there, and then if you put more and more particles, and depending upon the energy levels, then you have, you need to have the electrons. You cannot have the same type of same spin electron sitting in the same energy level. Whereas in case of bosons, you can have a possibility of all the particles going and occupying the same energy level, leading to what we call it as a Bose-Einstein condensate. Now, as you know, this phenomenon of the Bose-Einstein condensation, wherein the lowest energy level can be occupied by all the particles that you can put into the system, was predicted by, initially it was initiated by Professor Satyendranath Bose, where he actually wrote a paper on how this was in relation to the Planck's law and the explanation of the Planck's law with respect to the, whatever all the developments that were going on those days. And he came up with an idea of a completely different idea of how to explain this phenomenon. Now, I just translated something from this paper, which was initially written by Bose and was sent to Einstein, which he later translated it and sent it for publication in this prestigious journal. So basically, the phase space the hypothesis of energy of electromagnetic field existing in quanta of H, and how that can fill up the phase space for a given volume, which is basically divided into cells of H cube size, and how the possible distributions for this light quanta can be macroscopically defined for the radiation to be filled up in these different cells. It finally gives rise to, it can be used to calculate the entropy and does all the thermodynamic properties of this radiation. Now, this was a very a revolutionary idea of how to explain the Planck's radiation formula, and that kind of gave birth to the quantum mechanics. And I'm proud to see that this was some of the foundation stone was laid in India, by Bose here. Now, what happens when these particles, bosons, they go and occupy this lowest possible energy state? So the consequences are many different types of consequences. One of the early observed consequences of this Bose-Einstein condensation was in the existence of superfluidity in case of helium-4 when it's taken below a certain temperature, leading to all kinds of interesting properties like frictionless flow for the fluid and propagation of acoustic waves through this through the system and things like that, which led to all the explanation of that was given through the understanding or trying to explain the phenomena through occurrence of a condensation, a Bose-Einstein condensation of these helium, a fraction of these helium-4 atoms within the system, and for which it was awarded the Nobel Prize for Piotr Kapitsa in 1978. Now, the other consequence is in observation of superconductivity, where, I mean, of course, electrons are responsible for conduction of current in any metallic system. However, when due to some coupling between these electrons, the pairs of electrons behave like a composite bosonic particle, and it goes through what the Bose-Einstein condensation of these particles, of these paired electrons, leading to superconductivity. And this was first observed in mercury here by Kamerlingh-Onnes, and this was later explained through BCS theory and all that. But this was another example of the formation of Bose-Einstein condensation. Now, all these two examples of superconductivity and superfluidity were in naturally occurring systems, and where a part of the system, not all atoms, but a part of these atoms were undergoing this phenomenon of Bose-Einstein condensation. Now, in this case, there was no actual control of how one can actually change the number of particles in the state, or different properties can be engineered the way we want. Those kind of things were not possible at that time. However, it was predicted that this particular phenomenon, one should be able to observe, or one should be able to achieve in using a system of atoms, or for instance, in the case of dilute atomic vapors. So you take a collection of particles like atoms or even molecules, and then bring them to a situation, to a configuration where you put these particles together in some bottle or a vessel, and try to change the conditions of densities and temperatures such that the phase space density increases in such a manner that the de Broglie wavelength, which is given by the Planck's constant over the momentum of these particles, this de Broglie wavelength starts approaching the interparticle spacing of these particles. And one should be able to get to a situation where all these de Broglie wavelengths kind of overlap with each other, and they coherently add up and give a giant matter wave. Basically, all these particles, once they go into this Bose-Einstein condensate state, then you get a pure Bose condensate, which acts like a giant matter wave. However, when this sounds very simple, and people started working on this problem for a long time, since 70s and 80s, using initially the simplest atom, which is the hydrogen atom. And people try to achieve this Bose-Einstein condensation by increasing the density and lowering the temperature, etc. No, but if you take a gas of atoms or molecules, you know that once you start playing with the temperature and pressure, depending upon the interparticle potential, depending on the kind of atom that one chooses or the molecule that one chooses, one goes through different kinds of phase transitions. Maybe it will go into a liquid state or a solid state, which will prohibit you from achieving the Bose-Einstein condensation. So choice of the particles is an important thing, and people then turn to other techniques where one could actually use other techniques to lower the temperature. Instead of cooling hydrogen using cryogenic techniques, there were other techniques which people started exploring. Parallelly, there was this entire field of laser cooling and trapping of atoms which was being developed, wherein a gas of atoms was cooled using lasers, basically transferring the motional energy of the particles into the extra energy of the photons that are scattered by these particles when shown with light or laser light. Those techniques were being developed, and using those techniques, people started taking the atoms to lower and lower temperatures. And also choosing the right atoms was important, as I said, because if there is a strong attractive potential between the particles, then they would just stick to each other or form some kind of molecules or something. So people started working with dilute gases of alkali atoms like sodium and rubidium and also cesium. However, in those days, cesium turned out to be a bad choice because its scattering length did not allow them to achieve Bose-Einstein condensate. However, Eric Cornell's group, together with Carl Wyman and Wolfgang Ketterle's group, they were working on, Eric Cornell's group was working on rubidium atoms and Wolfgang Ketterle's group was working on sodium atoms. Now, these people could actually lower the temperature of these atoms in such a manner that the phase space density also could be jacked up to beyond 1 and get to this state of Bose-Einstein condensate. And this was achieved in 1995, and they were awarded the Nobel Prize in Physics in 2001. In 97, there was another Nobel Prize which was awarded for developing these techniques of laser cooling and trapping, which enabled achieving Bose-Einstein condensate in dilute atomic gases. Now, this is the first image which came up in the journal Science on the achievement of the Bose-Einstein condensate. As you can see, there are 3 surface plots of the densities of the atoms of about 10,000 atoms or so, where the first picture here on the left side, the first of the surface plots, which is at 400 nanokelvin. This is a density distribution of thermal cloud of atoms, which is more or less Gaussian in 2 directions. Now, as this sample of atoms goes through a phase transition, when it's cooled further, slowly the density in the center of this cloud of atoms starts shooting up. This is an optical density shooting up, and there is a sharp phase transition, and then you are left, after further cooling, you are left with only a pure Bose-Einstein condensate. Now, this was the first time that one could achieve a Bose-Einstein condensate using artificially created Bose-Einstein condensation by cooling atoms and engineering the phase space density the way one wants. And on the right hand side is a picture of an optical table where inside this coils here, there is a glass cell which is hidden, in which the atoms are actually trapped and laser cooled, and also cooled further in a magnetic trap. This is a picture of the sodium atoms Bose-Einstein condensate, which was produced at MIT by Wolfgang Ketterle's group. And they were the second ones to produce the BEC. However, they showed a lot of interesting experiments with this giant matter wave, the Bose-Einstein condensate, and some of them are just depicted here. One of them is generating a pulsed, extracting out this Bose-Einstein condensate in pulses of, a bunch of atoms from this Bose condensate. You can see here pulses of these Bose condensed atoms which are coming out. This is essentially extracting out, so one can think of this collection of atoms in the Bose-Einstein condensed state in a trap as a coherent giant matter wave, as I said. And by extracting small portions of it, it is like extracting out photons in a pulsed laser, in a pulsed optical laser. They termed it as a pulsed atom laser. And the second experiment is basically to show the phase coherence in this condensate. They actually split the condensate into 2 parts physically with an optical slicer, optical knife, and made them interfere with each other. And you can see here that in the bottom here, the black and white image, you can see stripes of black, the fringes here, which essentially is an analog of interfering laser beams. So this was a very important were very important experiments to show the properties of this phase coherence properties of the Bose condensed atomic sample. The other experiment that were shown, which were very interesting and which are analogous to the experiments that were seen in superfluid helium are this formation of vortices. Now, if you take a normal fluid and rotate the fluid, then it would just rotate like that. Whereas in a superfluid, there would be a discontinuity in the phase in one circulation here, and it will lead to this formation of these small vortices. And depending upon how fast you rotate the bucket in which the superfluid is held, in this case, it's the trap, where the trap asymmetry is rotated as a function of time, and you see this formation of vortices. And in the bottom here is a real image of the density changes in the atomic density changes. So wherever there is dark, there are no atoms because there is a phase singularity there around each of these vortices. Now, the setup that we have at IISER Pune, you can see a collage of the images of this setup where we produce this Bose-Einstein condensate regularly, and we produce this condensate in a crossed optical dipole trap, which is basically formed by focusing far of resonant optical field, which is not resonant with the atoms. And we trap the atoms in the intersection of these optical dipole traps and evaporate the atoms by lowering the trap so that hot atoms go away and we are left with colder and colder atoms. And in the top, you see the three images where there is a thermal cloud on the left side. This is a two-dimensional image of optical density of the atoms in the trap. And in the center one, it's undergoing a phase transition. And in the third image, you have a pure Bose condensate. So the optical density suddenly rapidly increases and you get the Bose-Einstein condensate of these atoms. Now, here is an image of how a Bose-Einstein condensate of dilute atomic gases is produced. This is not an image, sorry, this is a video here I'm going to show. So basically you start with atoms which are at more or less room temperature and then capture them in, before I show the video, I'll just summarize what this video shows. You capture these atoms in 6 laser beams, which are actually doing the laser cooling of these atoms from room temperature down to several hundred microkelvins. And then from there, at that point, the phase space density is still very low, of the order of 10 to the power minus 6 or minus 7. And then you cool these atoms further down by evaporative cooling and then increase the phase space density by lowering the temperature by throwing away the hot atoms and allowing the remaining atoms to rethermalize. So I'll turn on this animation. Now, before turning on, I should say that in the bottom side, on the left side, there is a sample of rubidium atoms here, which is heated, and there is an atomic beam that is generated, which goes across the... so you can see here the video. So there is a rubidium oven and there is a Zeeman slower where the atomic beam is slowed down with a counter-propagating laser beam. And these atoms which are there, which are going in the direction from left to right, they are slowed down with a laser beam which is going from the right to left. Basically, all the photons that are scattered by these atoms are going to reduce the velocity of the momentum of these atoms by the scattered photons, and the velocity keeps reducing as the atoms move towards the right. Now, as they move towards the right, they are going to go out of resonance from the light. To keep the atoms in resonance with the light, the Zeeman levels are modulated along the length by an axially varying magnetic field, which is generated by these coils, which has a specific shape here, so that the magnetic field falls quadratically as the atoms slow down, and they are always kept in resonance with the light. And hence, they continuously slow down from about 400 meters per second to the left to about 20 meters to the right, wherein these slowed down atoms will now get captured in the 6 beams, which is basically a magneto-optic trap. So these 6 laser beams from 3 orthogonal directions actually capture the atoms, which are the slowed atoms that are coming into the center here. And you get a collection of bunch of atoms of about a billion atoms. You trap them in about a centimeter volume at about a few millikelvins temperature. And you basically now turn off the laser beams because the light is also going to heat the atoms. So there is an equilibrium reached where the temperature kind of reaches Doppler cooling limit. Now, to cool the atoms further, we turn off the laser beam and transfer these atoms into either a magnetic trap or an optical trap. This is shown for a magnetic trap. where the atoms are transferred into a magnetic trap, purely in a magnetic bottle, using only magnetic fields. But before transferring, we do a spin polarization of the sample of these atoms by an optical pumping process. And then now the temperature is still few hundred microkelvin. The temperature is not low, and the phase space density especially is very low, 10 to the power minus 6 or 7. You need to go beyond 1. So what we do here is we throw away the hot atoms and then basically do an evaporative cooling, forced evaporative cooling, and increase the phase space density. Now, to do the evaporative cooling in a magnetic trap, what you do is you flip the spins so that they go into an untrapped state. This magnetic trap is like a magnetic bottle holding the atoms only if the spins are oriented in one particular direction. Now, we flip the spins of the outermost atoms by shining a radio frequency pulse, a radio frequency whose frequency is continuously changed, ramped down, so that the outer atoms are left, they leave the trap, and the remaining atoms, they kind of keep rethermalizing, and then the distribution comes to a lower and lower temperature. Now, you can imagine how this evaporative cooling works. So you take a Maxwell-Boltzmann distribution, you cut off the tail. Now, once you cut the tail, a few atoms in the tail, the remaining atoms are going to rethermalize, and the distribution is going to peak at a lower temperature. You continuously keep chopping off the tail, and you basically end up with lesser and lesser atoms, few orders of magnitude, like 2 to 3 orders of magnitude less atoms. So you start with 10 to power 9 atoms, you go to 10 to power 5 to 10 to power 6 atoms. But however, the phase space density increases from 10 to power minus 6 to more than 1, and then you get into a Bose-Einstein condensate. Now, at this point, the evaporative cooling is stopped, and then the cloud has, the atomic cloud has gone into a Bose condensate. Now, how do we know that it is in a Bose condensate? Now, this magnetic trap, it is not a symmetric trap in all 3 directions. It is like, in our case, it is like a baseball. So the atomic cloud in the trap takes a baseball shape, because the trapping frequency or the stiffness of the trap is larger in the higher direction and smaller in the horizontal direction. Now, what happens? So once you have a giant matter wave in such a potential, what happens is that, so the uncertainty, it's a giant wave function sitting in a harmonic trap, but the trap has different stiffness along 3 different directions. In the directions where the stiffness is larger, there the extension of the wave packet, spatial extension, is less, which means that from the uncertainty principle, the momentum extension is larger in the direction where the cloud is more compressed. Now, once you release the cloud from the trap, what happens is the cloud is going to expand more in the direction where the confinement is larger. So this is the confinement in the trap. Okay, you see the ellipsoid in the horizontal direction. Now, once you turn off the trap, the cloud is going to fall down under gravity, and its symmetry is going to change like that, because the momentum uncertainty in the vertical direction was more, because the spatial extent was less in the vertical direction, and hence the shape of the cloud changes. Now you do an imaging of this cloud with a pulse of light, and you get the density distribution of the atoms on a CCD camera. You measure the optical density, and from there you deduce the number of atoms and everything. Now, if it were a thermal cloud, this asymmetry in the cloud would not happen. However asymmetric the cloud is in the trap, it would basically expand symmetrically. And that is what shows here. So in this image on the left side, this is a thermal cloud. And once you release it in gravity, under gravity, when it's falling down freely, it expands symmetrically. It becomes a circular cloud. However, once it goes into a Bose condensation state, it expands asymmetrically depending upon the asymmetry of the trap in which the condensate was held. That is an indication of how the formation of the Bose-Einstein condensate. Now what? Of course, I mean, that was a remarkable achievement of producing a Bose-Einstein condensate in the lab. So, although in 1995 only 2 atomic systems were this phenomenon was exhibited on only two atomic systems like rubidium and sodium. Later, many other types of atoms were also used to produce Bose-Einstein condensate. For example, cesium atoms, lithium, potassium, and these were alkali atoms. And then there were rare earth elements like ytterbium, strontium, etc. were also used to produce Bose-Einstein condensate. Not only were neutral atoms in their ground state were used, atoms like helium atoms in their metastable state were also used to make a Bose-Einstein condensate, because metastable helium has a very peculiar characteristic, because the electronic state in which these atoms are existing, the metastable state, has a very large internal energy, about 20 electron volts or so, and they lead to other interesting phenomena that one can observe. Anyway, nevertheless, so once you make this condensate, after that, I mean, people started using this sample of atoms in a condensed state for many applications. Now, one of the interesting applications that was demonstrated in about 2002 was putting these atoms. Once you put these atoms in a three-dimensional or a two-dimensional optical lattice. Optical lattice is nothing but a periodic array of potentials that is created by interfering light beams in along three different directions. And people actually demonstrated solid-state systems, Hamiltonians that explain solid-state systems using these cold atoms in optical lattices. Basically, you can create a pure, you can take a pure system and test out all your Hamiltonians that play an important role in explaining the properties of various solid-state systems. And one of the things that was shown in 2000 through a breakthrough experiment was a superfluid to Mott insulator transition using rubidium atoms in a periodic three-dimensional optical lattice. And when the atoms are localized, there is no phase coherence between the atoms, and the image is here. And when the atoms are delocalized and there is a phase coherence, then you see in the K space, you see sharp peaks in the momentum distribution. So this was shown in this particular experiment. This was the first experiment to actually initiate experiments on using these ultra-cold atoms in a Bose condensate, and later even fermionic systems to be put in optical lattices to study various condensed matter physics problems. Another technologically important application is in demonstrating or building atomic clocks with, say, for example, in the recent time, ytterbium and strontium atoms put in an optical lattice are used for building an atomic clock. Of course, not everything here, what I show here is for using a Bose condensation, because atomic clock, you don't need a Bose-Einstein condensate. However, for things like building atom interferometry based devices, sensing devices, a BEC is required, because you need a giant matter wave, which is going to act like a laser based, like in a laser based interferometer, you use matter wave interferometer. You build a matter wave interferometer with optical fields acting as matter elements like beam splitters and mirrors to build these interferometers. One can study physics of Anderson localization, many body physics, and do all these quantum simulations using these extremely cold atoms in a Bose condensate for a variety of these experiments. Now, as I already showed you the video of producing the BEC. Now, the idea is, as I said, at room temperature, the de Broglie waves do not overlap with each other with these particles. But once you go through a phase space density, which is of order 1 and more, precisely in pure atomic systems, it needs to be above this 2.6 number. And lambda cube should be more than that. Then you get this macroscopic occupation of the ground state in the confining potential. Now, as I showed you in the video, in this particular systems, you basically start with laser cooling of atoms, and then you put them in either an optical trap or a magnetic trap, do an evaporative cooling, and get this Bose-Einstein condensate. Now, I'll show you one example of this Bose condensate as a matter wave being used for a technological application, or many such applications can be built using what is called as an atom-based interferometer. Now, as everybody, most of you might know, there is a Mach-Zehnder interferometer. Now, you can, in a Mach-Zehnder interferometer, okay, for a moment you assume that this is a Mach-Zehnder interferometer of light. You come with the light, then you have a beam splitter which splits the light beam into two paths, and then you have two mirrors here which deflects the paths, and then there is a final beam splitter where you merge the two split beams and then get a interference pattern depending upon what is the extra phase shift any of these beams would have gained along the path. So that's the traditional Mach-Zehnder interferometer which one builds using photons. Now, similar things can be done with matter waves. So, for instance, you take an atomic wave packet here, which is entering the interferometer. You apply what is called as a beam splitter pulse. In this case, it will be an optical field like a grating, which is applied on this incoming wave packet, which splits into two paths. One is a straight path and the other one where the atomic wave packet picks up a momentum and changes the path. And then these two paths, basically, I mean, the atomic cloud or the wave packets go into these two paths. And then you have these mirror pulses which deflect the atomic beams, atomic wave packets, and then get them, merge them back with another final beam splitter pulse. And then by measuring the population of these atoms, atomic wave packet either going in this direction or horizontal direction, you actually build a interferometer. Now, in such an interferometer, if you use atomic wave packets, there are a lot of things that can be done. One of the things is atoms being particles, matter particles. They can possess electric dipole moment. They can possess magnetic dipole moment. They possess mass. Now, depending on what you want to measure, for instance, if you want to make this interferometer sensitive to accelerations, gravitational accelerations, then you choose atoms where the magnetic dipole moment and also the electric dipole moment is not present, and then let these atoms' atomic trajectories evolve in free space under the influence of gravity, and measure the phase shift of these paths as a function of the acceleration of the gravity. Now, there will be phase shift which will be picked up by these atomic wave packets because of gravitational acceleration. And that, by measuring that, you can actually measure the gravitational acceleration very precisely. And the other thing is you can also build what is called as a Sagnac interferometer. Now, on the left side, I have a picture of an optical Mach-Zehnder interferometer, which is mounted on some rotating table. Now, if this table rotates, the fringes that you see in this detector produced because of the phase difference in these two paths of the light, that phase difference changes depending upon the omega or the rotational frequency of this table on which the Sagnac interferometer is, on this Mach-Zehnder interferometer is put. Now, this is called as a Sagnac interferometer, which is used to measure rotations of an object. For instance, the laser gyroscope is based upon this kind of principle, a Sagnac effect. Okay. Now, the change in phase is basically the phase shift that you gain when the table is rotating is proportional to the omega dot, the area that this particular interferometer covers, the area enclosed by this interferometer. Now, if you choose atoms instead of photons, the theoretical sensitivity that you get is about 10 to the power 11. Of course, the area that is covered with an atom interferometer is much lesser than what you would cover with, say, optical fiber based gyros or laser gyro. So essentially the sensitivity, if you use atoms, falls down to about a gain of about 10 to the power 3 to 10 to the power 4. So atom interferometers are showing a lot of potential to increase the interferometer sensitivity instead of using light. Now, as I said, if you use atoms, they can be made sensitive to background magnetic fields or electric fields or gravitational field. One example is building a gravimeter, okay, using these matter waves. So one can actually measure gravitational acceleration g with extremely high precision. Now, why is it important? What happens when you start adding more and more digits to the measurement of g? Of course, in high school, we know that g value is 9.8. But then if you start adding these digits, you can become sensitive to many things going around you. One is, if you change the latitude, if you go to a different latitude on the earth, the value of g changes in the second place. And then if you change the altitude, it keeps changing in these different places. But as you can see, the most important application is in this measurement of the underground density and in underground water resources. So as the underground water content or water resources, this thing density changes, then you start becoming sensitive in this particular decimal place. Of course, you can also see the effect of the moon going over you, the tidal effect at this particular seventh decimal place, for example. Now, this particular device is very important for a technological application, as I said. So these are the various applications of this gravimeter. And of course, if this measuring it to these so many digits is only possible with giant matter waves, and in this case, using a Bose-Einstein condensate. Now, these applications range from civil engineering to even strategic applications like detecting underground tunnels, etc. Now, these atom interferometer-based devices, including the gravimeter and the rotation sensor, can be used for things like inertial navigation, GPS-free, for instance, for navigating undersea without the use of GPS signals, for locating underground tunnels, for example, and also for doing many fundamental physics experiments like the fine structure constant, gravitational constant, testing the equivalence principle, etc. These atom interferometers are very useful. Now, what one does in doing this atom interferometer is, so one takes a Bose-Einstein condensate. So these are the images from the lab, in my lab here. So a Bose-Einstein condensate, and then by applying Raman pulses, which actually transfer a portion of these atoms coherently into higher momentum state. Here in this case, it's 4 times h bar k. It's basically 4 photons are absorbed by a portion of this wave packet, and it goes into a different direction. So this is 0 h bar, the wave packet which has not picked up any momentum, and a wave packet that has picked up some momentum. And then again you apply another pi pulse and deflect these atoms, and apply a final pi by 2 pulse for doing the measurement of these populations in the 2 different paths. The image that I had shown you in the beginning of a Mach-Zehnder interferometer, this is how you see in the lab by application of different pulses of light gratings to actually see the final population. Now, by changing the phase of the final pulse here, pi by 2 pulse, you can actually see a nice oscillation in the population in either the 0 h bar k, 0 momentum state, or the higher momentum state here, and you get a nice fringe here. Now, how does one use this for measuring gravitational acceleration? So as a function of height here, you take a Bose-Einstein condensate and then let it fall under gravity. Okay, it is falling under gravity. As it's falling under gravity, the height changes like that. Now, while the height is changing, you apply 3 pulses, pi by 2 pulse, where you split the wave packet into a wave packet going up and wave packet just falling down. And then you apply a reflection pulse where you actually, as it's shown here in this, after a time period of t, you apply a reflection pulse, and the wave packets again reverse their trajectories and they fall down. And then at some point they will merge they will come to each other. And then there you apply a third pi by 2 pulse and then do an imaging of the populations. Now, what happens is that as the wave packets are falling down under gravity, they're picking up an extra phase. Now, this phase has to be compensated by changing the frequency of by changing the phase of the final pulse that is applied to these atoms, or final or even the middle pulse. So you have to keep up with the changing phase as they're falling under gravity. Now, how much phase you are changing, by measuring that, and by changing that compensating phase that you have to keep up with to keep the population same in the final detection, you measure the gravitational acceleration. So that is how it is. That is how the final phase is done. So this is an interferometer signal. Now you sit at so this on the x-axis, it is a chirp rate of the frequency. basically the phase that you have to change in order to keep up with the changing acceleration, with the phase that is picked up due to the acceleration. And then if you sit at a position where there is no phase change, basically for all the interferometer times. So by changing the different interferometer times like this T, if you keep varying, then there is a fringe where there is no change in the position of the fringe. So there you sit and measure the fringe very accurately, and you can go and measure this gravitational acceleration to the highest possible sensitivity. Now, currently our sensitivity has approached of about 2 times 10 to the power minus 6 in delta G by G with an interferogram time of 10 milliseconds. Now, we are in the process of pushing this by 3 orders of magnitude, and then this would be one of the state-of-the-art gravimeters. However, the applicability of this interferometer, right now it's a complete lab. The applicability would be there once that everything is made into a more compact device. Now, this is where we are. As I said, we want to move here. So this, we are hoping to get that. The other experiment that we have been doing is generating a continuous, well, this is a CW quasi-continuous atom laser. So the reservoir here is a reservoir of the Bose condensed atoms, as it is shown on the left side. So there is a BEC in an optical dipole trap, and we extract a coherent beam of these atoms, which is basically a giant matter wave beam of these atoms extracted out of the Bose condensate by playing with the magnetic trap and the optical dipole trap, and essentially getting out a small beam of these atoms. Now, this is an atom laser, an equivalent of laser for matter waves, and this has tremendous potential. However, there has been a huge challenge in producing BEC continuously. However, just last week, a few days ago, after a decade-long work in University of Amsterdam, Professor Florian Streck has demonstrated continuous production of Bose-Einstein condensate. I don't have the slide, but it came in last week's Nature, that they could produce in a continuous fashion a Bose-Einstein condensate by continuously loading a trap with the cold atoms and evaporating them and producing a BEC. Now, if they succeed in extracting those atoms continuously, then that would be a huge technological breakthrough in generating an atomic atom laser, the so-called atom laser. Now here we have a kind of quasi-continuous atom laser. We can produce it for about 500 milliseconds and then redo the BEC for a few seconds and produce it. The idea is to use a continuous atom laser to produce a continuous interferometer like with light beams. Okay, so that's all I had to say, and these are my former students and the current students who have been setting up different experiments in the lab. We have this rubidium BEC experiment, and there is this strontium atomic clock and distributed quantum information processing system that is also that's another platform which some of these students are involved in. And all the funding for my lab has been through the institute and Department of Science and Technology, and some funding from CSIR over the years. And I have been collaborating with my colleagues Santanam, Rajesh and Pawan on different aspects. And yeah, thank you. If you have any questions, please.
Really excellent overview of the field, and starting from the very basic, very latest state of art that it's going. So, are you okay with taking a few questions?
Yeah, sure. Please go ahead.
Oh, so are there questions, comments?
I'm just curious to know about two atoms in a standing mode, when it in which condition it will act like a molecule. So basically, the production of molecule from the condensed atom, something like that. So what is the status of that kind of research?
Yeah. So I mean, there are many groups who are working on studying a formation of molecules through cold collisions at very low temperatures. So the idea is, I mean, there are a couple of ways in which these molecules can be produced, depending upon, okay, one has to have a detailed understanding of the interatomic potentials between the species that you are interested in, and how to get them into a bound state. Now, there are two different broadly used methods for producing the molecules at very low temperatures. One is through either through an optical Feshbach resonance or through a magnetic Feshbach resonance, or one can use photo association. So you go from you use two photons. One photon, I mean, basically these two photons connect a state of two colliding atoms. You have a potential that one can draw when the atoms are approaching, and then you come with two photons which will connect through an intermediate state to another state where you create a bound state. So the extra energy will be the difference between the two photons that you use and generate add that binding energy into the system and create a molecule. So that is one way to do that. And of course, the other thing is through a magnetic Feshbach resonance. So you play with the Zeeman energies of the spins of the atoms, and then by sweeping the magnetic field, you go from a free state to a bound state. And people are trying to create molecules people have created molecules between cross species like rubidium potassium, rubidium cesium, and some other systems where the electric dipole moment of these molecules is very high, and that is projected to be used for doing quantum information processing kind of for those kind of applications.
Okay, thank you. I think there is another question.
Yeah, hi, Vakan.
Hi.
Excellent talk.
Thanks.
Yeah, so I was just wondering about your this G measurement.
Huh.
See, how much the anisotropy in your this molecular or atomic condensate when it falls, there may be asymmetry, right? So how much that is going to play a role in measuring the G?
What kind of asymmetry you're saying?
So when it is falling, I mean, like when it is forming the condensate,
Huh.
when it is falling, there may be a asymmetry, right? I mean, because it's a big mass, and if it's not uniformly distributed, how much it is going to play a role in your measurement?
Right. So it will not affect so much because we measure the relative populations in the ground and, well, in the two momentum state. And of course, each measurement is done many, many times because the number is not guaranteed to be same in every measurement. There is a fluctuation of about 10% in the total number of atoms. There is the asymmetry. I didn't exactly understand the kind of asymmetry that you're talking about. I'm assuming you're talking about the number of atoms that are different in the two wave packets, right?
Yeah. But when it is falling, of course, you have to know the potential, and then it's falling, right? I mean, and it's a parabolic potential you are using.
Yeah.
So isn't there is some asymmetry in the structure? Because you have a different gradient if you are taking vertically. While falling, it may create some kind of asymmetry in the system.
Oh, yeah. So the thing is, one has to, when we go to more decimal places, one has to be very careful in what you call in choosing the vertical direction, meaning the vertical beams that are used to actually split the wave packets that in the vertical direction has to perfectly match the direction of the G. So that will introduce some errors. Now to do that, we have to introduce what are called as tilt meters and other things in the bottom of the experiment. So those things have to be taken into account for sure. Yeah.
Thank you very much.
Yeah.
Thank you. Are there questions from the online participant? You can just unmute and ask the question if you have one. Mohammed,
May I ask?
Yes, sir, please.
Yeah, hi. So this is again regarding the measurement of G from the application point of view. So since there are so many factors, G is so much sensitive to various factors. Now, when you want to measure a specific property for a specific application, how do you remove the contributions due to other factors? So how do you calibrate?
Yeah, so one has to go for what is called as a gradiometer configuration. So you measure the gradient of the gravity. So you take two atomic clouds and launch them in two different directions and measure the gradient of the gravity. That will help in getting rid of some of the common factors that can affect your measurement.
So what I was trying to ask is, since you said that, so it might depend on the density of the rock or the presence of water. There are different. Then you have to detect whether there is a water present or not. But the density of the rock may be different.
Right. So this.
I'm trying to.
Yeah, this one so you have to have supporting additional data from other types of measurements also. For instance, some ground penetrating radars data and other things you need to have at the same time. Gravity gradient, gravity, and additional supporting data you need. This alone won't be useful, and they alone won't be useful. Sure. They have to be put together.
Okay, thank you.
Okay, Mohammed, I have just a curiosity, very naive curiosity. You just said that the Bose-Einstein, initially these were all rubidium, rubidium, etc. Later on, people have been strontium and all others, some heavy FTP. So, what is the challenge? Why we cannot think of anything in the periodic?
Yeah. So okay. So the fundamental principles that are used for cooling these atoms are laser cooling, using lasers to cool the atoms. Now you need to have atomic systems. Even recently, people have succeeded in cooling molecules using lasers, which has been a biggest achievement. The problem is molecules is a different ball game altogether because it's a complicated levels and levels that are involved. But even if you take simplest atomic systems, then you need basically some levels where you can excite the electron, and the transition is a closed transition. So when you shine it with light, there should be a possibility of those levels to scatter photon. I mean, like in sodium, you have the 58, the orange color light between S and the P state. There is a large cycling rate of photons that will lead to cooling down the atoms. Now, there are some atoms where you need additional lasers because once you excite it to the excited state, maybe, wait, let me see if I have something. Yeah, you see here, you see this slide here. This is for a rubidium system. So this S half to 5P half. This is the laser cooling transition. Now, once you shine a laser on this, you should have a fast cycling between. So atoms should go to the excited state, come back to the same ground state. They should not go to some other state. In this case, there is a small fraction which goes down to the other hyperfine level, but that can be cleared using a repumping laser. Now, you should essentially have closed optical transitions within an atom to be able to use laser cooling. Okay, so that is first important thing. And the second important thing for getting a Bose-Einstein condensate is you need to have the right scattering length. You should not have a scattering length where in such a manner that the atoms will stick to each other once you cool them down. So that's the thing that is important. You need to have closed laser cooling transitions, and depending on how you want to further cool it, there are other things like whether it will have whether you can trap it in a magnetic trap or not, whether you can trap it in a dipole trap or not. All these technical issues come into picture, and you get restricted to only a small number of atoms from the periodic table. You don't want atoms where your lasers are in such crazy wavelengths that it's impossible to produce those wavelengths, like in extreme ultraviolet or something, or very, very far infrared, things like that. So those dictate which can be used, which system can be used, which cannot be used.
still, I think, one last question.
No, I think that this is for alkaline and alkaline earth metal is better to use this.
Yeah, alkalis and alkaline earth metals are so far used, and then there are these rare earths also. Some of them like dysprosium, erbium, and chromium. They are of interest because they have large magnetic dipole moment, which is for other exploring physics of basically large dipole moment atoms. Those are also those are also used for different types of experiments, but getting a condensate and then doing those experiments.
Okay, thank you, Makan, once again for this really nice experience.
Thank you very much. Thank you very much for inviting. Yeah, thank you. Bye. Bye.